this segment, we're going to talk about copy mechanisms and pointer networks. And this is going to leverage the same kinds of ideas from attention, but enable us to actually go even further in terms of consulting the input and using that when generating our output. So to start off with, we're going to look back at this example about Pont de Buis and focus on actually how we generate this token Pont de Buis and how we would do this correctly. Now, recall that we've set up this attention mechanism, which computes this weighted sum over the input and then produces a distribution over the vocabulary in this way. And the problem is we're actually kind of screwed because our vocabulary doesn't even contain Pont de Buis, right? Like, I mean, unless you had some massive vocabulary, it wouldn't be in there. And the attention mechanism can't really bail you out in order to predict a word that's just fundamentally impossible to predict. And even if it were in the vocabulary, I mean, the attention still is kind of reckoning in terms of these embeddings, and you need to kind of you need to kind of compress the input into this good C vector and then have that actually be set up correctly in order to generate the right token. So there's a couple of issues here, and we're going to see how to solve them with a mechanism that we call pointer networks. So the standard decoder, which is what we've seen so far, is something that we're going to call pvocab. And this is the softmax over the vocabulary, and it assigns, at least some probability to every word, right? It might be very small, but it places a distribution over this vocabulary with support everywhere. So the idea behind pointers is that they are going to predict based on the source words instead of the target vocabulary. And the way that's going to work is the following. It's going to look similar to the attention mechanism that we've set up, but this attention pointer is actually going to govern what the output is. So we have a distribution here over values for yi that is proportional to, or log proportional to, you need to exponentiate this stuff and normalize it, so you need to do a softmax here, but it's log proportional to hj transpose times v times h bar I. And what this is basically saying is, okay, we're going to form a distribution over these source encoder states as well, and that distribution is going to place probability mass on the possibility that we generate wj, the corresponding word from the source, as the output here, yi. And so the way to think about this is that instead of taking the attention distribution and using it to map down the encoder outputs, the encoder LSTM outputs into a single vector, now what we're doing is we're taking that distribution and actually using it, combining that with the words in the input, and using that to place a distribution over what we can generate here. All right, so the cool thing is that we can actually combine these two ideas. We can introduce a intermediate probability variable called pcopy here, and we can set up a mixture model where our generation output, p of yi given, whatever, is a mixture of p pointer and p vocab. And so what the model can then learn to do, if we predict pcopy based on, various factors like the decoder state, we can say, all right, the model can dynamically switch between either generating from the vocabulary or copying from input. And so I'm going to kind of draw that like this, where we've mixed these two distributions together, the green one and the blue one. So we have support everywhere, but we also have the ability to kind of boost these words that show up in the input and learn how to do a better job of copying them. And so it can kind of do both of these skills, and now it can flexibly adapt between them. Okay, but what we still haven't done is we still have not expanded the vocabulary. However, now we can do this pretty easily. So for example, what we do is we take our input vocabulary, which is this thing at the top here, the, a, blank, blah, 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 up to zebra. And then for a particular example, we can add a couple of tokens to the vocabulary, Pont de Buis and Ecotax here. And now our copy mechanism allows us to actually assign these some probability. So the pointer, the pointer mechanism allows us to assign these some probability. So the vocabulary generation can still only place a distribution over the things on top, because you have this matrix of parameters W that's going to specify, essentially parameters for predicting each possible output word. But the copy mechanism, which looks at the input, can now say, okay, I really want to copy word 5. And if word 5 is Pont de Buis here, then it's going to be able to assign that some probability, and we're actually going to be able to predict it. All right, so in the Jia and Liang work, they incorporated this kind of copy mechanism, which has since been used in other work, for example, due to Abby C. at Stanford, which we'll talk about when we get to summarization. And in their work, they found that it actually made a pretty big difference for this GeoQuery and this ADIS data set for semantic parsing. So copying was really helpful for them to be able to get these associations between tokens in the input and tokens in the output. So it's sort of a useful thing. What we're going to see is that there's actually a lot less emphasis these days on copy mechanisms. By breaking up words and turning a word like Pont de Buis into a series of smaller units, it turns out that we can actually do a pretty good job of predicting a sequence of those small units, even if it's a sequence we haven't seen before, just using the attention mechanism. So we'll unpack how that works a little bit more later, but basically, you won't actually need to implement copy mechanisms that frequently. Attention is, going to be able to do most of the work for you. But it's still a very nice idea for how to think about incorporating this expanded vocabulary, copying over stuff you haven't seen before, and drawing on these ideas from attention to make our encoder-decoder models more flexible. And that's the end of the segment.